In this video, we're going to look at lesson 1 for our next unit, but first we're just going to recap some similarity before we go too much further. So just remind ourselves that there's a whole bunch of different ways you can set up the proportions when we're looking at similar triangles, and whatever way you decide is best for you is fine. You don't have to set it up any other way. So there's just 4 different examples here. Just to look at one of them, like we have AB is 4, and DE is 8. So notice that those are the same spots of the triangle. And then we have CB is 3, and FE is 6. So you can notice that both of them simplify to 1/2. We could cross multiply and see that they both equal to 24, but then we know that they're proportional. The same would work for the other pieces as well. So it doesn't matter which method you're more comfortable setting them up in, as long as you find a way that works for you. So speaking of similar triangles, let's look at exercise 2 here. We're talking about a person who's 68 inches tall that casts a shadow that is 54 inches long. And at that same moment, a tree is casting a shadow of 18 feet long. And we want to determine how large the tree actually is, or what the height of it is. So just keep in mind, anytime we're talking about height, we're talking about right triangles. Because when you're a person standing and their shadow, remember, the person's going to make a 90-degree angle with the ground always. So while they're 68 inches tall, the shadow is always on the ground for that 54 inches. And it doesn't have to be a perfect triangle, like my 54 and my 68, it's not really drawn to scale, but that's totally okay. You'll never lose points for drawing your triangle however you choose to. But then we have another triangle with a tree and a shadow. We're looking for how big the tree is, but the shadow is 18. So we have to be careful and realize that there's something wrong about this right now. I don't know about you, but I don't know how often a tree shadow would be smaller than a person's. The thing we have to keep in mind is the first time we were dealing with the person's in inches while the tree is in feet. So I have to take this 18 and I'm going to convert it so it matches the other 2 units I have of inches. So I'm going to take 18 and I'm going to multiply by 12 because there is 12 inches in 1 foot. So that's going to get us 216 inches. Now that I have this, I'm going to go ahead and tell you to pause the video and you set up a proportion. So set up the proportion and try to solve for the height of that tree right now. I set up my proportion as 68 over 54 equal to x over 216. You could have something different. That's totally fine. As long as you ended up with x equal to 272, you set up your proportion correctly. But the problem is I wanted my answer to the nearest foot. So right now, this is my answer in inches. So if I want to go back to feet, I'm going to divide by 12. And when I divide by 12, we end up with 22.6 repeating. So I round that up to 23 feet. So 23 feet is our total answer. We want to make sure we have our units shown in there, and we want to be sure that we're in the right unit. So I could have converted in the beginning and made the 68 and the 54 into feet as well, but I just didn't want to deal with decimals personally until the end. So that's why I chose to do it this way. We're going to look at something else like that in exercise number 3. So now we're dealing with right triangles again. What's happening here is that we're trying to find the length of a river, or the width of a river, rather. Now, you could try to throw a ruler down. You could try to throw a tape measure and try to get it that way, but it's not always so going to work as nicely. It could be too large. So engineers usually use similar triangles to set up these proportions to determine how large this river would be. So you'll notice that they use perpendicular lines, which tells us that we have 2 right angles right off the bat. Now, once I know that I have right angles, the first question is asking me how I know these triangles are similar. So first off, I know angle B is congruent to angle D. We know perpendicular lines form congruent right angles. We see that they're right angles, so we have all right angles are congruent. So we know that. So we already have 1 pair of angles in this case. Then on top of that, anytime you see that X pattern, that intersecting lines, we know we have vertical angles. And vertical angles are always congruent. And that's my second pair of angles. So now by angle, we would know that those triangles are similar. As soon as you have two pairs of corresponding angles that are congruent, then we know we have angle. We would have that third automatically, but we don't have to show it. So let's look at what we're given in this case. We know that BD, this whole length, is 225. We know CD, this smaller piece, is 30. And we know DE here is 12. Our goal is to determine what AB is. So one thing we got to be careful of, though, is this BD. BD is not a part of my proportion because BD is both triangles combined. So we have the smaller piece is 30, and then that whole thing is 225. So we're going to subtract that to get BC. So 225 subtract 30 ends up being 195. So now I have all four sides that I would use for my proportion. Go ahead, pause the video again, and then determine what the length or the width of the river is. Notice everything is in feet this time, so you don't have to worry about changing any units. Okay, welcome back. So the way I set up my proportion was x over 195 equal to 12 over 30. Again, yours could be totally different, but when I cross multiply, I should end up with x equal to 78. As long as you ended up with 78 feet as your final answer, then you set up your proportion correctly. So you don't have to worry about changing it. You could keep it as long as you ended up with the correct value of 78, and you remember to label the units as feet. Now, I went a little bit ahead here in exercise 4, and I filled in the pieces that we knew. So I'm given that we have two similar right triangles. I have AB is 15, EF is 16, AC is 17, BC is 8. And then I was able to fill in this table for a triangle ABC because it was all these pieces. BC was 8 over AC is 17. Then I got 15 over 17 and 8 over 15. But so then I'm going to look here. I'm already told that I'm dealing with two similar triangles. So I'm going to look at the corresponding ones, 8 and 16. So I'm thinking from getting from 8 to 16, that means my scale factor is going to be 2, which means DF is going to be 34 when I multiply 17 by 2, and 15 by 2 times 2 is 30. So now I know D is 30 and DF is 34. So just like the other ones now, I can set this up to be 16 over 34, 30 over 34, and 16 over 30. What I do want to be careful about, though, is that these all simplify. So I can simplify this to 8 over 17, 15 over 17, and 8 over 15. And you'll notice that these two things are in the same exact proportion. Now that makes sense because we know the triangles are similar, but this is also tying to a special property about right triangles, which leads us directly into our next unit. So we're going to start talking about trigonometry. Okay. Now, trigonometry, the biggest thing I could know about trigonometry is this phrase right here, SOHCAHTOA. And I'm also going to write it over in the side here a little differently. Sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangents equal to opposite over adjacent. So sine, cosine, and tangent are all my trig functions. That's what's new. Now, I just want you to know before we even get any further, this only works with right triangles for what we're doing right now. So the only way we can set up these ratios is if we're dealing with right triangles. So notice that sine, cosine, and tangent are all talking about angle A here. So from angle A, the opposite side is going to be the one that doesn't actually touch the angle, the one that's across. So the opposite side is BC. The hypotenuse is always the largest side of the right triangle, and it's across from the right angle. And then there's one other side, the adjacent. Adjacent is next to the angle, but not the hypotenuse. So now that I have those pieces, I can set this up. So like we said, sine of A is equal to opposite over hypotenuse. So BC was the opposite. Hypotenuse is AC. Cosine is the adjacent. So I'm I'm talking about AB over the hypotenuse of AC, and tangent is the opposite over the adjacent this time. Now, it might make a little bit more sense if we look at it with actual numbers. So I'm going to go in here, and we're going to look at exercise 5. Now notice for A, B, and C, we're all directly talking about angle R. So the opposite side is going to be the side that doesn't touch the angle, so that's TS. The hypotenuse is always across from the right angle, and the adjacent is next to my angle, but not the hypotenuse. So that being said, for sine of R, opposite is 5 over the hypotenuse is 13. The adjacent is 12 over the hypotenuse of 13, and the opposite is 5 over the adjacent is 12. And that would be for angle R. Now, it changes directly for D, E, and F because we're talking about a different angle now. Angle T. So the opposite's going to be the 12 this time because that's the side that doesn't touch. And the adjacent's going to be next to at that 5. But the hypotenuse doesn't change. Because remember, in a right triangle, it's always the largest side across from the 90 degree. So now, sine of T, the different angle, is 12 over 13. Where the cosine is 5 over 13. And tangent of T is 12 over 5. And we'll look more about those relationships a little bit later. But it always matters which angle we're going from. Okay, so let's look at the next one, exercise 6 here. So we have the sides given for this right triangle, QRS. We have QR is 8, QS is 17, and we want to determine the value of sine of Q. So first thing, I'm going to write out SOHCAHTOA again. And I'm going to get in the habit of writing this out anytime I need it. Okay, so I know I'm talking about sine of Q. So from this angle, I have my opposite. I know this is the hypotenuse, and this is the adjacent. So if I look here, though, opposite over hypotenuse, I'm missing the opposite right now, and I need it and able to solve for this. So think about how we find a missing side of a right triangle, how we've done it all the way up until this point. Well, we use Pythagorean theorem. So I'm going to have x squared plus 8 squared equals 17 squared. And I'm going to go ahead and solve through that. We're going to have x squared plus 64 equals 256. I'm just kidding. Sorry, that was 16 squared, 289. When I subtract, we get x squared equals 225. And when I take the square root, we get 15. So this side here is 15. Now the only thing left to do is write it out as sine of Q is equal to the opposite side of Q is 15 over the hypotenuse of 17, and we're done. We leave it just like a ratio here. You'll notice that it's overlapping two ideas for us. So we're talking about trig because we can see cos and tangent in the answers, but it's also talking about similar triangles. So remind ourselves for a second, triangle ERM is similar to triangle JTM. Remember, they're always in a specific order. Notice that angle M is both the right angle, so I know that E and J are congruent and R and T are congruent. So that being said, J is equal to E. So if I look here, it's talking about RM, which is part of the triangle that has E in it, just like RE is as well. But from angle E, it's the same as angle J, like we did in the one on the first page. But from RM is the opposite over the hypotenuse, which would be sine, not cosine. So that one's out. For R, for cosine of R, it's the same as angle T. And then JM, though, is the opposite, and JT is the hypotenuse, so that would be O and H again, also out. So then if I look at the other two, it's going to work. is choice 4 because that's opposite over adjacent.